In this video, I want to discuss the sums of the angles of triangles. All right, and we're going to find out that the sums of all the angles, three angles of any triangle, always adds up to the same measure. Okay, 180 degrees. All right. So the way I'm going to prove that is I'm going to draw a arbitrary triangle. It doesn't really matter which kind you draw, what type. Draw it resting on a horizontal line, and then to prove what I'm going to want to do is I'm going to want you to draw a parallel line that touches the very top vertex. Okay, so there we go. And let's call the angles, let's call them angle A, angle B, and angle C. So our goal is to figure out what is the measure of angle A plus the measure of angle B plus the measure of angle C. All right, so here we go. Now we know from what we learned about parallel lines cut by a transversal, we know that alternate interior angles are congruent, so that means that these two angles are congruent because I'm interpreting the line segment AB as a transversal. I can also interpret line segment BC as a transversal, and I will get that this angle is the same as that one. All right, so what that tells you is that this angle right here is equal to it has the same measure as angle A, and this one right here has the same measure as angle C. Okay, so check this out. And this one, of course, has this measure of angle B. So apparently the three angles that are making up the straight angle at the top are the same measures as the triangle angles. Okay, so that is the proof. So this right here, this straight angle, just like every straight angle, is 180 degrees in measure. Okay, and for any triangle, you can always draw vertical, and you'll see that the three triangles will add up to make a straight angle if you put them adjacent to each other. Okay, so there's the proof. You always get 180 degrees. Now, what are some implications of that? All right, well, let's say that I had two triangles, and let's say that I knew that these two triangles had two corresponding angles that were the same. All right, so for example, maybe this one's 40, this one's 40, and we know those are the same, and maybe we've got this one is 60 and that one is 60. So you'll see us whenever we have a pair of corresponding angles that are congruent, we'll refer to that with the letter A. In this case, we have two corresponding pairs of angles that are congruent, so we'll call that AA. All right, so the question is, if I have AA, what about the third one? Is that congruent, or is that the corresponding pair there, is that congruent or not? Do we have AAA, in other words? Well, because they always add up to 180, you know that there's not much choice for the third angle. We've got 40 and 60, so this one has to be 80. There's no other possibility. Likewise, the other one has to be 80. So what this means is if you have two angles that are the same, then you can be assured that you always have three pairs of corresponding angles that are the same. Okay, we can prove that from the fact that all three angles, the measures add up to 180 for every triangle. All right, now so you might want to write that down. That's a fact that drops out from what we started with. Now let's focus on right triangles. All right, so I have a right triangle. We know that the right angle is 90 degrees. Okay, and so the other angles, whatever they are, we don't know what they are. Different right triangles will have different acute angles, right? However, we know that both of the sums of the acute angles, we know that all three angles have to add up to 180. We already have a right angle, so that means the two remaining angles have to add up to 90, right? Because the whole thing has to add up to 180. So that means that they have to be, the fancy word for that is complementary. So let me type this one out. The two acute angles of any and every right triangle are complementary. All right, so you can take that to the bank. All right. Okay, what about if we had a right isosceles triangle? Okay, so what we just said is still going to be true about for a right isosceles triangle, but there's going to be a stronger condition that we can say. So we have a right triangle, it's isosceles, so that means that you have two sides that are the same. Maybe these are length 3 and length 3, all right? And in that case, it'll turn out that both of these angles are the same. All right, I won't prove that now, but you can see from symmetry that if you chopped this isosceles triangle, let's say in half this way with the blue line, both halves are the same. So since both are exactly the same, that means that those two base angles have to be the same. So there's a symmetry proof for you. Now, all right, that's all well and good, but the point I wanted to make is we know that all the angles have to add up to 180. So the only choice now is 45 and 45. Because to meet those conditions that they're both the same and all three angles add up to 180. Okay? So a right isosceles triangle is a 45 45 90 triangle. All right? Now, let's show that equilateral triangles have you can only have an equilateral equal angular triangle with 60-degree angles. All right, so equal angular, and so all three angles are the same. They all have to add up to 180. So the only way that they can be the same and add up to 180 is if each angle is 1/3 of 180. So that means 60. Okay, there's no other choice it could be. If it's equiangular, which later on we'll learn also is the only angle it could be for equilateral. Okay. All right, and then the last fun fact I want to mention about that we can derive from the fact that all the angles add up to 180 for every triangle is the following. I want to introduce the idea of an exterior angle. So if you have an angle, if you have a triangle and you extend any side, all right, then you will create this angle that's outside the triangle. That's called an exterior angle. And you can do this with any side of the triangle. In fact, let me go ahead and, just to show you, let me go ahead and extend another side. Let's extend this one this way. All right, and if we did that, then here's another exterior angle. Okay, and then I could extend the third side. All right, so you can see that there's lots of exterior angle choices that you can have. Lots of ways to make exterior angles for a triangle. All right, now what I want to show you is that the exterior angle is, the measure of the exterior angle is always equal to the measure of the sum of the measures of the non-adjacent sides. All right, so let me focus on, well, let me give names to each of these. Let's call this angle A, B, and C. Okay, and let's call this exterior angle here, let's call that angle X. Okay, now would you agree? I hope you would agree that the measure of all the angles of any triangle, in this case A, B, and C, is equal to 180. Please say yes. Okay, now, do you see that angle C and the exterior angle X make a straight angle? All right, and we know what the measure of a straight angle is, right? So the measure of angle X plus the measure of angle C has to be 180 as well, right? Okay, so now notice that both of those equations have the same right side, and they both have an angle, measure of angle C on the left side. The only way that that could be true is if this right here, this box and this box are the same, right? Because you're adding them to the same measure, the measure of angle C, and getting the same number. So look at what I've just shown you. I've just shown you that angle X is equal, the measure of angle X is the sum of the two non-adjacent sides of the triangle, A and B, okay? And so you can apply this same reasoning for the other exterior angles. Let's call this one Y and this one Z. So by the same reasoning, the measure of angle Y has to be equal to the measure of angle B plus the measure of angle C. All right? The measure of angle Z has to be equal to the measure of angle A plus the measure of angle C. That's a condition derived from the fact that the sums of all the angles, three angles of a triangle, add up to 180.